precipitation, which is on the x-axis, and we would regress that against one of the water quality variables. In this case, it's turbidity. Calculate a regression line, and then the scatter of the points around that line and how tightly they fit the line gives us an idea of the strength of the relationship that we're looking at. So if those points are scattered willy-nilly across this XY axis plot, that would show that it has a very low strength in that relationship. And what you're seeing here is a higher strength relationship. And then to get an idea of the responsiveness of the particular water quality variable to the climate variable, we were looking at the slope, and that gives us an idea of the relative responsiveness. Now, you can essentially calculate this for every pair of variables. You can average them, standardize them so that you take the bias out of some of the comparisons in the way the slope and the strength of relationships are represented in these individual analysis comparisons, and come up with what we call a biophysical sensitivity index. And this is how that index sort of distributes around the country, red being a very high biophysical sensitivity to climate change, and the blue dots being very low. There really is no major national trend that we can see in biophysical sensitivity around the United States. Tijuana and Sapelo Island were the two reserves that were pulled out as being fairly highly sensitive when it came to looking at this relationship between these climate change variables of precipitation and temperature and changes in water quality parameters at those particular reserves. So, essentially we think that what this points out is that there are a lot of local factors driving water quality changes, not just the climate patterns that we were seeing in the data. Two other things that we looked at were